Okay, so on to some new examples. We're going to use something called ICE chart. That would be ICE. ICE charts will be used when things are not at equilibrium. So when you're asked about something that's not at equilibrium, you have to do an ICE chart. ICE stands for initial change equilibrium. Initial change equilibrium. Okay, so first thing you want to do, and I didn't need to mention this until now, but you really want to think about is everything at equilibrium, yes or no? If everything's at equilibrium, you do your K expressions and you crank out and you go. So as you read the prompt, the question prompt, if things are at equilibrium, you see the word equilibrium all over, it says that things are at equilibrium, then you're just going to do K products over reactants raised to their powers, right? Whether it's pressure or concentration. So in this problem, it talks about just this guy being at equilibrium. So as you look at these problems, the next few examples, you want to always be in the mindset, well, any of the problems, honestly, when you're solving for either a concentration, a pressure, or a K, you want to be able to evaluate whether or not things are all at equilibrium, some are at equilibrium, none are at equilibrium, whatnot. So let me walk you through some of that thinking, and I'll try to give you some good prompts to think about. So going in as this is a problem on a quiz, I can see that it tells, I see this word initially. That's going to give me an indicator that I need an ICE chart. Okay, so I'll talk about what an ICE chart is here in just a moment and show you how to do that as we get going. So give me just a moment. Okay, sorry about that. I'm back. I apologize for that delay. Okay, so as I look at this problem, I see that it talks about, I've got this as my chemical equation. And I have some moles of PCl3, I have some moles of PCl5, I have a volume, I have some moles of Cl2. So right off the bat, I kind of know that I'm probably going to need to be dealing with K, and I will be needing to do square brackets or moles over liters. Okay, so it says calculate equilibrium concentration for all species and the value of K. So that's what we got to do. A couple things. We're going to get all of these concentrations, so we're going to get moles over liters for all these at equilibrium, and we're going to get the value of K. Remember, K means things are at equilibrium. Q would mean something that's not at equilibrium. So the first thing we have to do is consider what we would be solving for. Once we're at equilibrium, our expression would be K equals PCl3 times Cl2 over products over reactants, PCl5. So once these values are all at equilibrium, we can plug them in. Notice that this only has one of the three, Cl2, at equilibrium. It tells us that PCl3 and Cl5 are not at equilibrium. So therefore, we have to get them to equilibrium before we can plug them into K. If they were already at equilibrium, we'd simply solve moles over liters and plug them in here. But because it tells us their initial values, not equilibrium values, we will have to figure this out. So first thing we're going to do is we're going to think about the concentrations, because we know no matter what, we have to have concentrations here, because we have either concentrations or pressures. So we're going to think about what's the concentration of PCl3. To do that, we're going to take moles over liter. So PCl3 is 0.298 moles over your 5.00 liters. I'm going to calculate all these here in just a moment. I'm going to set them up first. And then we're going to have to figure out what Cl2's concentration is. Because again, I can't plug moles in here. I got to have concentration. So we know the concentration for chlorine would be calculated by 2.00 times 10 to the negative third moles over 5.00 liters. And then we have PCl5, which we can calculate by taking its moles, 8.70 times 10 to the negative third moles. Let me expand my screen some here. Over 5.00 liters. Okay, so for all of these, we can get concentrations. I'm going to do that next. I will take in my calculator then for PCl 3.298 divided by 5.00, and I'm going to get 0.0596 big M. I'm going to take 2.00 EE to the 3 negative divided by 5, and I'm going to get this one to be, I'm going to write it underneath here just so you can see it better, 4.00 times 10 to the negative 4th big M. I'm going to take 8.70 to the 3 negative divided by 5, and I'm going to get, for this one, 1.74 times 10 to the negative 3rd big M. I'm going to go ahead. So this would be 5.96 times 10 to the negative 2 big M. Okay, so once we have concentrations, and some problems you may already have concentrations given, sometimes you'll have to convert moles to liters, sometimes you'll have to go from grams to moles to liters, and sometimes you will have pressures. So once you've established your concentration or your pressures, I highly recommend you go back in and decide for each one, is it an initial value or is it an equilibrium value? So I look back up here and I see that the PCl3 and the PCl5 are both given to me at initial. So I'm going to put an I here, and this one is an I down here. And Cl2, as I read this, I believe I might have read that earlier wrong, but Cl2 is at equilibrium. So that's going to be an E for this concentration. So that's a very important, crucial step, that you identify if the concentrations or pressures are I's or E's, meaning initial or equilibrium based on the word problem. So again, I know this is an initial because I know by reading this PCl5 is initial. I know that PCl3 is an initial, and I know Cl2 is equilibrium. So I, E, and I. Okay, I had to stop the video and I fixed a few things. What did I fix? I had an equation here with the ice chart. I hadn't explained that yet, so let me erase that, so ignore that if you had noticed it a moment ago. So this is how you would do it. So the first thing you're going to do is calculate your concentrations or pressures and establish whether they're at I's or E's, meaning are they at equilibrium or are they at initial. Then you're going to take your chemical equation, you're going to rewrite it in some space. Ooh, that's big fat. Let me fix that, apologize. And you do not need to worry about states of matter when you write this, but you do need to be aware of what they are as you're building your ice chart. So you put the balanced chemical equation, and you can put a double arrow or single arrow, I don't care, and you're going to put I, C, and E down here. Then you're going to put underneath of these, if they are aqueous or gaseous. If they were a solid, you just put an X, right? But solid or liquids. But because aqueous and gaseous, AQ, things with AQ or G at the end of them will be used, we will see what we have. So this is the initial row. We're looking here to see, do we have an initial value of PLC5? No initial value of PLC5. What do we have? Well, we go down here and we had marked that as initial. So this is going to be 1.74 times 10 to the negative 3rd. Do we have an initial value of PCl3? Yep. 5.96 times 10 to the negative 2nd. And we do not have an initial value of Cl2. We read the word problem. We established that what we had for Cl2 was the equilibrium value. Okay, so now the change part will be the key piece here. The change part absolutely is important, and you have to know how to know which direction the change is. So what the change is going to be either a plus or a minus X. Even more specifically, it's going to be a plus coefficient X or a minus coefficient X. So these all have ones in front of them, so they'll be plus or minus X. Here is how you will do the next. So either side, right? Thinking of this as your reactant side and this side of the arrow as your product side, we'll have, so the plus x will be together. So one side will have a plus x, the other side will have a minus x. You won't have a plus and a minus x on the same side of the arrow. You will not have a plus and a minus x on the same side of the arrow. So what you're thinking about is, what does plus mean? Plus would mean that we're increasing, we're adding. We need to increase this side to get to, this is 0. I have to have some of this before it can flip back and start making this. So this is going to be a plus x and a plus x. Okay, so thinking about them as units, plus x and plus x, y plus, because I have to increase, I got to get this before it can flip back and make some of this. So this is plus x and plus x. Okay, and there's a 1 here technically, and a 1 here technically, because the coefficients here are 1 and 1. Okay, all right, so then that by default will make this side a minus x. Why minus x? Technically a minus 1x. Why? Because minus because the other side's plus, and the 1 because there's a 1 for a coefficient. So then you're going to think of it like this. And if you recall, we haven't done anything with that value of equilibrium. So that's going to go down here underneath the CL. So this is going to be, and I like to leave space. This is sort of my method that I have seen the most success with. Okay, so I put my concentration here, but notice I left space above it. That's important. Okay, that's important. So now what you're going to do is to get E, E is I plus C. So in this case, for this one, it's 1.74 times 10 to the negative third minus x. And this is going to be 5.96 times 10 to the negative second minus x. And this is going to be 0 plus x. So all of these are going to be solved for. Now, I have to know what x is to get any of these. But if you notice this value right here, 0 plus x equaling this, then we know x equals 4.00 times 10 to the negative fourth. Okay, so now we know x here. So then we're going to take 1.74 times 10 to the negative third minus my x, which we know to be 4.00 times 10 to the negative fourth. I promise I'll get neater with this writing. Just using this pen is a lot different. Okay, so then this is going to be 4.96 times 10 to the negative second minus 4.00 times 10 to the negative fourth. So we're going to figure out what these are. We already know this value here was already at equilibrium. We calculated it from the beginning. We're going to get these two values by using this method. So I'm going to take 1.74 to the 3 negative minus 4.00 to the 4 negative, and I get 1.34 times 10 to the negative third. And then I'm going to take and do this part next. 5.96 to the 2 negative minus 4.00 to the 4 negative. And I get this one to be 5.92 times 10 to the negative second. Now I have an equilibrium value for this one because it's down in my E spot, and I have an equilibrium value for this one. Okay, next thing will be is that now that we have E's, we can plug them into K and solve. That's the next thing I'm going to show you. Let me pause for just a moment and we'll continue. Okay, now that we have established our equilibrium values, we got to plug them into this expression. Because remember, in order for it to be K or KP and not a Q here, you have to have equilibrium values to plug in. So I'm going to give myself some space. I'm going to leave that visible. So then I'm going to be able to say, okay, now K equals, I'm going to do PCl3. So my PCl3 is 5.92 times 10 to the negative second times CL2. CL2 was 4.00 times 10 to the negative fourth over PCl5, which is 1.34 times 10 to the negative third. Okay, so let's see what that is. All right, so we're going to take 5.92 times 10 to the negative 2 times 4.00 times 10 to the negative fourth, hit equals, divide by 1.34 times 10 to the negative third, and we should get K to be 1.77 times 10 to the negative second. So now we have solved for all the pieces the question asked for. It asked for the concentrations at equilibrium. We've done that. We already had one at equilibrium, but we had to use the ice chart to get the other two because these were originally initials. We had to get equilibrium values by using the ice chart. And then we could plug those into our expression, which is up a little bit on the screen right here, right? That's what I did here. And I was able to solve for my value of K to be 1.77 times 10 to the negative second.